Alright, jumping back to example number 10. Somehow I missed getting that one in the notes. You're given this situation where you have a parabola, y equals x squared, and you are looking particularly when a particle is moving along this path and it's at the point 2 comma 4. So I put that on the picture. And you know that the x coordinate is increasing at a rate of 6 centimeters per second. So you know dx dt is equal to 6, which makes sense because as you're moving away from the origin, x is getting bigger. And you want to know how fast the distance between the particle and the origin is changing at that point. So I've drawn in this line z. That's really what we're looking for. How fast is that distance changing? I'm not looking for dy dt. I'm actually going to be looking for dz dt in this problem. So I'm going to set this up as I have every other related rates equation. First, I'm going to use a known equation that relates the variables that I have. So again, I'm going Pythagorean theorem that x squared plus y squared has to equal z squared. Unlike in the related rates problem for the latter though, in this case z is not constant, z is changeable because as x and y both change, so does z. So I have a dx dt, a dy dt, and a dz dt this time. I'm given in the problem dx dt is equal to 6. And I also know that this is occurring when x is equal to 2 and y is equal to 4. So I know those particular values. And what I'm trying to find is dz dt, the rate of change of the distance from the origin to the point. Well, one of the things I probably should also notice that if x is equal to 2 and y is equal to 4, that I can calculate the value of z using the Pythagorean theorem. That would simply be 4 plus 16 or the square root of 20. So I also do know the value of z at that instant. So prior to plugging any values in, let me go ahead and generate a related rates equation that I would have 2x dx dt plus 2y dy dt, and that has to equal 2z dz dt. And I can go through and cancel out all the 2's. Those will all cancel out. So I really have x dx dt, y dy dt, z dz dt. And I'm going to try to solve for dz dt. I'm given dx dt, and you'll notice that in this particular problem, I do not know dy dt. Uh-oh, that's a problem. Except I do have a relationship that's given to me in the problem. I do know that y is found by taking x squared. That y is x squared. So maybe if I could go back into my problem and eliminate the values of y and instead use all values of x and z, then I wouldn't have to worry about dy dt. So let's pretend for a second I did not do this. And let's rewrite our initial equation as x squared plus y squared, where y is equal to x squared, so x to the 4th equals z squared. Now I would have 2x dx dt plus 4x cubed dx dt equals 2z dz dt. And now I have a related rates equation that is all in terms of x and dx dt and no dy dt's. And since I do know the values of x and I do know the value of z, I should be able to find dz dt. So by taking all of this information that I have from here and substituting it in, I can find dz dt. And when you end up doing that, you end up getting that dz dt is equal to 54 radical 5 over 5 centimeters per second. So you should go ahead and go through the math and verify that in fact you can get that. But in a lot of related rate equations that you see, you may feel that you don't have enough of the information, so you're going to be looking for that dy dt, and you're not going to be able to find it. It's not going to be given to you in the problem. So go ahead and substitute in for y the values of x squared and then get everything in terms of x, and then you'll be fine. So that's how you go about doing example number 10.